Imagine, if you will, a star. Not just any star, but the crushed, incredibly dense remains of a star much more massive than our own sun. These are neutron stars. They are some of the most extreme and fascinating objects in the entire universe. They push the laws of physics to their very limits, challenging our understanding of matter itself. Think of them as cosmic laboratories where nature conducts experiments under conditions we can only dream of replicating here on Earth. They are tiny, yet they pack an astonishing punch. These stellar remnants are truly compact giants. A typical neutron star might only be about 20 kilometers or roughly 12 miles across. That's about the size of a city. You could drive across it in less than half an hour, if you could somehow survive the journey. Which, spoiler alert, you absolutely could not. But here's the mind-bending part. Into that small space, a neutron star crams the mass of about 1.5 times that of our sun. Our sun, which is over 1 million times the volume of Earth, squeezed into a space you could practically walk across. The matter within a neutron star is so densely packed that it behaves in ways that seem utterly alien to us. It's a soup of neutrons, particles usually found locked inside the nucleus of an atom, now pressed together with unimaginable force. The gravitational pull at the surface of a neutron star is hundreds of billions of times stronger than Earth's gravity. If you could stand on one, you'd be instantly squashed into a thin film of atoms. These are not gentle giants, they are powerhouses of extreme physics. So, why do we stare out into the cosmic darkness, searching for these enigmatic objects? Because they hold clues to the fundamental nature of matter, the life cycle of stars, and the very fabric of space-time. Neutron stars are like lighthouses in the cosmic ocean, their extreme properties illuminating the path to deeper understanding. They are the universe showing off, demonstrating just how wonderfully strange and complex it can truly be. Join me as we journey into their world. The story of a neutron star begins with the death of a giant. Not just any star, but a massive star, many times heavier than our own sun. These behemoths live fast and die young, burning through their nuclear fuel at a prodigious rate. For millions of years they shine brilliantly, fusing lighter elements into heavier ones in their fiery cores. Hydrogen becomes helium, helium becomes carbon, and so on. Up the periodic table. It's a delicate balance, this stellar alchemy, a constant tug-of-war between the outward push of nuclear fusion and the inward pull of gravity. But all good things, even for stars, must come to an end. Eventually, the massive star exhausts the fuel in its core. It can no longer generate enough outward pressure to counteract its own immense gravity. The core, now primarily iron, cannot be fused further to release energy. At this point, gravity wins. Catastrophically. The core collapses in on itself with incredible speed, shrinking from the size of Earth to the size of a city in mere seconds. This sudden, violent collapse triggers an explosion of unimaginable power, a supernova, as the outer layers of the star are blasted outwards into space in the supernova, creating beautiful and expanding nebulae. The core continues its dramatic collapse. The pressure becomes so immense that it overcomes the forces that keep atoms apart. Electrons and protons, the fundamental building blocks of atoms, are crushed together. They merge to form neutrons. Imagine squeezing all the empty space out of atoms, then squeezing the atoms themselves. The result is a core composed almost entirely of neutrons, packed cheek by jowl. This is the birth of a neutron star. This formation process is one of the most energetic events in the universe, second only to the Big Bang itself, or the collision of other compact objects. The supernova explosion scatters heavy elements forged in the star's heart across the cosmos. These elements become the building blocks for new stars, new planets, and perhaps new life. So, in a very real sense, the violent death that creates a neutron star is also a source of cosmic rebirth. It's a dramatic, awe-inspiring cycle of stellar creation and destruction. Let's talk density. The sheer density of a neutron star is almost impossible to truly comprehend. A single teaspoonful of neutron star material would weigh billions of tons on Earth. That's more than all the cars, all the buildings, all humanity combined, squeezed into something you could hold in your hand, if your hand wasn't immediately obliterated. The atoms are gone. Only a sea of tightly packed neutrons remains, forming what physicists call neutron degenerate matter. It's a state of matter so extreme, it's unlike anything we can create or experience on our home planet. This incredible density leads to an equally incredible gravitational field. the escape velocity from a neutron star. The speed you'd need to escape its gravitational pull is about half the speed of light. Light itself struggles to leave its surface, its path bent by the intense gravity. Time, as predicted by Einstein's theory of general relativity, actually ticks slower near a neutron star compared to time further away. It's a place where the fabric of space-time is significantly warped, a true testbed for our understanding of gravity in its most extreme form. Many neutron stars are also known for their incredibly rapid rotation and powerful magnetic fields. As the massive core of the parent star collapses, it conserves angular momentum, much like an ice skater pulling their arms in to spin faster. This results in neutron stars spinning hundreds of times per second. Their magnetic fields can be trillions of times stronger than Earth's. These rapidly spinning, highly magnetized neutron stars can emit beams of radiation from their magnetic poles. If these beams sweep across Earth, we observe them as pulsars, cosmic lighthouses blinking with astonishing regularity. The interior of a neutron star is still a profound mystery. While we know the crust is likely made of iron nuclei and a sea of electrons, deeper down, the pressures are so immense that neutrons themselves might break down into even more exotic particles, like quarks. Some theories suggest the core could be a quark-gluon plasma or even strange matter. Scientists use observations of neutron stars, their cooling rates, their spin, their behavior in binary systems, to try and peek inside these ultra-dense objects and understand the fundamental forces at play. Neutron stars aren't the only type of stellar remnant out there in the cosmic graveyard. For stars less massive than those that form neutron stars, but more massive than our Sun, their end-of-life story leads to a white dwarf. White dwarfs are also incredibly dense. A teaspoonful would weigh several tons, but they are supported against further collapse by electron degeneracy pressure, a quantum mechanical effect. Neutron stars, however, are far denser and more compact, supported by neutron degeneracy pressure, a much stronger force needed for their greater mass. Think of white dwarfs as the little siblings, dense but not nearly as extreme. What happens if the collapsing core of a dying star is even more massive? If the core's mass exceeds about 3 times the mass of our Sun, not even neutron degeneracy pressure can halt the relentless crush of gravity. The collapse continues, unchecked. The result is an object from which nothing, not even light, can escape: a black hole. A black hole is a region of space-time exhibiting such strong gravitational effects that it warps space to an infinite degree at its center, a singularity. So, in the stellar remnant hierarchy, neutron stars sit between white dwarfs and black holes, representing a critical tipping point in the battle against gravity. Studying neutron stars is crucial for advancing our understanding of the universe. They are natural laboratories for extreme physics. The conditions within them, the densities, the pressures, the magnetic fields, are far beyond anything we can replicate on Earth. By observing neutron stars, we can test the limits of our theories of gravity, like Einstein's general relativity, and learn about the equation of state of matter at supernuclear densities. This tells us how matter behaves when crushed beyond the confines of atomic nuclei. Ultimately, the quest to understand neutron stars is part of humanity's broader quest to understand our place in the cosmos. These objects reveal the universe's capacity for creating phenomena that are both beautiful and terrifyingly powerful. They remind us that there is still so much to learn, so many mysteries to unravel. Each new observation, each new insight into these cosmic powerhouses brings us a little closer to comprehending the fundamental workings of the universe we inhabit. And that in itself is a journey worth taking.